So before we start to actually apply Newton's laws in statics problems, it's really important first that we establish some critical common notations that we're going to utilize throughout the rest of these lectures. So whenever you're solving an engineering problem, it's really important that we first designate and assign a coordinate system. A lot of times we're going to be dealing with three-dimensional problems, but again, because we're just starting out, we're going to actually be focusing almost exclusively on two-dimensional problems. And so we'll typically be using an XY coordinate system, as you can see here, XY. We're going to define basically anything that's going in this direction as positive X. If it's going in this direction, that'd be negative X. And then if we're going down, minus Y, plus Y. When we have rotations, we're going to have counterclockwise rotations as positive. Clockwise rotations will be negative. So if we rotate, again, in the clock direction, it will be negative. So these are kind of our common notations and coordinate systems that we're going to use. If you use something different, that's fine, but you want to indicate that somewhere on your problem. So whenever you see a problem, just write out X, Y, positive sense, and then you can even say counterclockwise, positive, or you can just put a positive like that here. So indicate that usually at the top left-hand corner of our problem, and it'll help, again, because we do this, again, to keep us organized and to make sure that we can communicate our solutions to others that are looking at it. Additionally, there are going to be some critical assumptions and idealizations that we're going to utilize a lot in statics problems. In particular, we're going to make a particle assumption, meaning that we are going to assume that a particle has mass, but we will effectively ignore the geometry of a particle. So our particle will have some mass, but we're just going to ignore if it has some kind of strange geometry here. We're just going to treat it as a mass. There's going to be essentially some mass to this problem. One of the big critical assumptions that we're also going to make is a rigid body assumption. So when we say rigid body, the body is rigid so that when there's a force applied to our body, so for example, a beam, we are going to assume that there's going to be no deformation. Our beam will not deflect. So that's a big assumption that we're going to make in statics problems. Now you may say, and therefore material properties don't exist. You may see this may seem unrealistic, but again, we're actually going to see that it holds quite well for a lot of real life problems. And this is something that happens a lot. Again, we make idealizations, we make assumptions, and then we do experimental tests to ensure and see if they're accurate. If they're not, then we're going to have to include and actually examine those material properties. And finally, concentration of force, meaning that we're going to assume that when I have a body like this and I apply some force or some load, it's going to be concentrated at a single point in space. So it will be localized. Localized is a good word, meaning it exists and it's localized only at that particular point. So, fantastic. Next time, we're going to talk about force as a vector or first-rank tensor property, and we'll see you then. Thanks. Bye.